everybody, welcome to the second lecture of the week. This one is on mass percent composition. So we're going to go through two different topics today. We're going to figure out how to get from grams of a compound to grams of a single element. And then we're also going to learn how to figure out the mass percent composition of each element in a compound. So kind of two different topics today. So the first one, we're going to learn how to convert from grams of a compound to grams of an element. So this is just an example. It says hot packs are used to reduce muscle aches, inflammation, and muscle spasms. A hot pack consists of a bag of water containing an inner bag of 10.2 grams of calcium chloride. When the bag is smashed, the calcium chloride dissolves in the water and heat is released, which is really cool. But the question is, how many grams of chlorine are in the 10.2 gram calcium chloride bag? So here's kind of our scheme of how we are going to get through this. We're going to go from grams of calcium chloride to moles of calcium chloride, and we're going to use the molar mass to get there. So that's what we were talking about in the last lecture, that we can get from grams to moles of something using the molar mass. And then once we get moles of calcium chloride, we can use this mole factor to get from moles of calcium chloride to moles of just chlorine. So that is how, that's what we were learning in the first lecture of this chapter, where we had, okay, for every 1 mole of calcium chloride, there were 2 moles of chlorine in that compound, right? Because of this 2 there. So that 2 is telling us this 2. And then once we get to moles of chlorine, we can get to grams of chlorine using the molar mass. Again, what we were doing last time. So we're combining like the first lecture that we did with the second lecture that we did to get this one. So hopefully you're really, really solid at all of those pieces so that now we can put them together. But if you'll look, this is going to require us to do 3 steps in this train track. So it's quite complex. So make sure we get a good handle on it. So here are some equalities and conversion factors. So like I said, there are 3 steps that we're going to do. So these are what we're going to use for those 3 steps. Okay, so for the first one, we're going to convert, from grams of calcium chloride into moles of calcium chloride. And the way we're going to get there is that we know 1 mole is equal to the molar mass. And again, the way that we're getting this mass of calcium chloride here is that we know there is, calcium and there is chlorine. There's 1 calcium, 2 chlorines. We can multiply them by the masses on the periodic table. And then once we do that, we can add them up. And again, this unit is grams per mole on the molar mass. So that's where that number is coming from there. And then we can write our, conversion factors. We can put it on the top or the bottom, right? We can go forward. This is the one I was talking about on the last slide. Oh, this should say moles of chlorine there. That is a typo. Sorry about that. But for every 1 mole of calcium chloride, we have 2 moles of chlorine. And again, that's because of this 2 here. That 2 is telling us this 2. And then for the third step, we'll use the molar mass of chlorine on the periodic table to get from grams of chlorine to moles of chlorine. So this is going to be a good long problem. So here we go. How many grams of chlorine are in the 10.2 gram calcium chloride bag? So in the beginning of our train track, we will write 10.2 grams of calcium chloride. So the first step, like we said, we need to get from grams of calcium chloride to moles of calcium chloride. And the way that we are going to do that is we're going to use the molar mass. And so here we need grams of calcium chloride on the bottom, so this has to be grams of calcium chloride. And so when we have this grams of calcium chloride here, that is the molar mass of calcium chloride. So that is the number that's going to go on the bottom. So from the previous slide, we decided that was 110.98 grams of calcium chloride, and the molar mass is always equal to 1 mole. So that will go on the top here. Okay, and then we double check grams of calcium chloride cancels grams of calcium chloride. And now we have converted into moles of calcium chloride. So now we need to get from moles of calcium chloride into moles of just calcium, because at the end we're going to need to figure out grams of, not of calcium, of chlorine. We need to get from grams or moles of calcium chloride to moles of chlorine. So the way that we are going to do that is we're going to use that mole ratio. Okay, so we talked about that on the last slide, where for every 1 mole of calcium chloride, there were 2 moles of chlorine because of this 2 here. Okay, so moles of calcium chloride must cancel moles of calcium chloride down to the right. So this left side will go on the bottom. So for every 1 mole of calcium chloride, you will have 2 moles of chlorine. Okay, so now we've changed moles of calcium chloride into moles of chlorine. And the way that we figure out how to get grams of chlorine from there, we'll use that molar mass again. So I'll finish this, grams of chlorine. So molar mass here, for every 1 mole of chlorine, we know it's the mass of 35.45 grams of chlorine, and that's from the periodic table. So moles of chlorine has to cancel moles of chlorine down and to the right. So 1 mole of chlorine will go down here, and 35.45 grams of chlorine will go on the top. We double check moles of chlorine cancels moles of chlorine, always down and to the right. And then finally, we have grams of chlorine in this top right, which is what we were trying to find. So yay, we're done writing our train track. So now we can actually go through, multiply all the numbers on the top, divide by all the numbers on the bottom, and you will get 6.52 grams of chlorine. So I know this was a really long problem, but this is kind of the way that you will always figure it out. Okay, so you'll need to take your grams, convert it to moles using the molar mass. Then you'll use moles of your compound to get to moles of your element, and you'll use that mole ratio, right, that we're showing up here at the very, very top. For every 1 mole of calcium chloride, we had 2 moles of chlorine. And then we're going to use the molar mass again to get from moles of chlorine to grams of chlorine. So anytime you're converting from grams to moles or moles to grams, you're going to use the molar mass. If you are converting from moles of something to moles of something else, then you're going to use this thing up here. This is called the mole ratio. Okay, it's telling us for every 1 mole of calcium chloride, we have 2 moles of chlorine. So this was a pretty tricky problem. It's just combining a lot of things all together that we've been working on. So this is a practice problem for you. This is for you to try it out. So if you feel like based on that last problem, you have enough to go on, right? If you can get from grams of sodium chloride to grams of sodium, I recommend you pause here and give this a try. I'm going to go over it in just a second. But like I said, try it out on your own. See if you can do it. All right. So now we need to get grams of sodium chloride, and we're going to get grams of sodium. So I'm going to make myself a plan up at the top. Whoops. So we need to get from grams of sodium chloride, and at the end, we're going to try and get grams of sodium. So we can't go directly from grams of one thing to grams of another thing. We're always going to have to convert to moles and use that mole ratio. So we're going to go grams of chlorine, and we're going to turn that into moles of sodium chloride. Grams of sodium chloride, moles of sodium chloride. And then once we get moles of sodium chloride, we can convert to moles of sodium. And then once we get to moles of sodium, we can get grams of sodium. So if that was all the help you needed, if you just needed kind of like the plan, go ahead and pause here and try it out from there. But it's always going to be the same thing. Grams to moles, moles to moles, moles to grams. Always going to be that same thing. So if you're still stuck, here we go. Or if you're just wanting to see the answer. So we're going to start with 737 grams of sodium chloride. Up here, actually, I'm going to move, no, that's okay. Up here in the top left, that's what we're starting with, right? And so grams of sodium chloride has to cancel grams of sodium chloride. And we know from the scheme that I wrote at the top, we are trying to convert it to moles. And so we're going to use the molar mass to get here. So that is 1 mole of sodium chloride is equal to the molar mass. And that's going to be in grams. So the molar mass here is 58.44 grams. So the way that we got that is we add together sodium and chlorine. Since there's one of each, we can just add them up. So here, because we have grams of sodium chloride on the top, so we need to cancel down to the right with grams of sodium chloride, which means this right side is the one that's going to go on the bottom. So we put 58.44 grams of sodium chloride, and that means that 1 mole of sodium chloride will go on the top. So now we've converted from grams of sodium chloride into moles of sodium chloride. Now, to get from moles of sodium chloride to moles of just sodium, we are going to use this mole ratio. And if we look, for every 1 mole of sodium chloride, we have 1 mole of sodium, because there's no subscript here, right? There's no subscript, which means it's an imaginary one. So for every 1 mole of sodium, we have 1 mole of sodium chloride, we have 1 mole of sodium. 1 mole of, so moles of sodium chloride has to cancel moles of sodium chloride down and to the right. So we'll put this left side of our equality down on the bottom, 1 mole of sodium chloride. And then the 1 mole of sodium will go on the top. Moles of sodium chloride cancels moles of sodium chloride. That leaves us with moles of sodium. Now, to get from moles of sodium to grams of sodium, again, anytime we're getting from moles to grams or grams to moles, we're always going to use the molar mass. So here, this is going to be another molar mass step. So we're going to use 1 mole of sodium is equal to 35.45 grams of sodium. And I'm getting that number from the periodic table. Okay? So now we can put 1 mole of sodium on the bottom, and we can put 35.45 grams of sodium on the top. So then we're going to double check, and we're going to make sure, moles of sodium cancels moles of sodium. And then we are left with grams of sodium up on the top, which is what we were looking for. So now we can type that whole thing in our calculator. 737 times 1 times 1 times 35.45 divided by 58.44 divided by 1 divided by 1, and we will get 447.07 grams of sodium. Lots of sodium. So there you go. That's how you do it. But always make yourself this little scheme at the top. That'll help to get from grams to moles, moles of sodium chloride to moles of sodium, and then moles of sodium to grams of sodium. So these are long problems, but hopefully I've tried to make them a little bit more straightforward. So here is just kind of a summary of what we've worked on in general. So you can read through this at your leisure. It just kind of tells you how to get, if you're trying to go from grams of an element to moles of an element, you're going to use the molar mass. Same thing for compounds, right? And it tells you how to get between all of these things. So this is a summary of all the conversions that we have doing pretty much in total for Chapter 7. So there you go. So go ahead and pause here and try problems 27 to 30 on your lecture worksheet. And also, I know it says 10. We actually skipped number 10 before. I'm sure some of you noticed. It's just kind of out of order in your lecture worksheet, but now you should be able to do it just fine. So go ahead and pause and try those problems. Go ahead and check your answers on that lecture worksheet key when you have time. So on to the next bit. So this was kind of our second topic that we had to cover today, which is mass percent composition. And it says, given the mass of an element in a compound, we can calculate the mass percent composition of that element. And the way that you do that is you take the mass of the element, you're going to divide by the total mass of the compound, and then multiply it by 100. And this is the multiplying by 100 is to actually get it into a percent. Otherwise, this would just be a fraction. So we're going to go through practicing how to do this. Okay, so we'll have to calculate the molar mass, right? And so we've been actually working on that lately. The key here is that this mass of each element, make sure that this is the total mass. So not just the atomic mass that you got from the periodic table, but say there's more than one of that element, we're going to, multiply it by the total number of those elements. So this will make sense once we actually start going through it. Most people don't find this part too challenging. They find the first portion of the lecture more challenging than this mass percent composition. So like I said, it'll make more sense with examples. So here's one. It says the odor of pears is due to the organic compound purple acetate, which is this. What is its mass percent composition? So this would be how your problems will show up. And so we'll figure out the mass percent of carbon, the mass percent of hydrogen, and the mass percent of oxygen in this compound purple acetate. So here's how we do it. It's very similar to finding molar mass. So the first thing you're going to want to do is actually go through and find the molar mass, just like we were doing before. So in propyl acetate, we have carbon, we have hydrogen, and we have oxygen. So we have 5 carbons, 10 hydrogens, 2 oxygens. And we're going to multiply those by their masses on the periodic table. So carbon will be times 12.01, this will be times 1.01, this will be times 16. So when we multiply all those out, all right, so now we have the molar mass of propyl acetate. So this will help us to get the mass percent of carbon, hydrogen, and oxygen. So the way that we get the mass percent of carbon, we will take the total mass of carbon. So not this 12.01 that we were using earlier, but the total mass of carbon in the compound. So that will be that 60.05 that we're seeing there on the right. So 60.05 divided by 102.15, which is the molar mass. So we're taking our total mass of carbon, right? And dividing it by the molar mass of the compound. And then we're going to multiply this by 100 to get the percent. So when we do that, we are going to get 58.80% carbon. So that would be one of our answers. Then we're going to go through and we are going to do this for all of the elements. So that's our percent of carbon. So now we're going to go through and find our percent of hydrogen. So again, we're going to put our total mass of hydrogen on the top here, 10.10 over 102.15, right, that molar mass. And we're going to multiply by 100 to get the percent. So this is going to be 9.87% hydrogen. And then finally, we'll go through and we'll get our percent oxygen, and we can put our total mass of oxygen on the top. We can put our molar mass on the bottom, and then multiply by 100. And so that will get us 31.33% oxygen. And so just to double check, to make sure that you've done this right, thinking about, percents, all of our percents should add up to 100. So if you're really into checking your work, that would be what I would do. So at the very end, it should add up to 100 or pretty darn close. If you get 99.99 or 100.01, those count as being 100. Those are just due to rounding errors since we're rounding after 2 decimal points. So that's a really good way to check your work, to figure out what is, are you doing this right? If they don't add up to 100, you've done something wrong along the way. Here, I was going to point out, if you want to include, you can put grams for all of these, but you don't need to. If you don't include them, it's fine. If you do include them, cool. But essentially the reason I don't include them is because those units are going to cancel out throughout the course, right? Because grams divided by grams, they go away. So either way, whatever makes you happy. So here's just kind of a link to the environment. We can figure out, the percent. Oh, I've actually taken out all of these, but you can figure out the percent nitrogen, right, in fertilizers. So this is if you actually go back and look. I'll just include this here. Look at the slides that I've posted. Sorry. But different fertilizers have different percent of nitrogen in them. So like if we had NH3, the percent of nitrogen is 82.27% nitrogen, which is really high. But if you had something like this one, this is ammonium sulfate. If you went through and calculated the percent nitrogen in that one, it's a lot lower. It's 21.20%. And so farmers and whoever else is using these fertilizers will actually pick which one is best for their crops based on their percent nitrogen. So I promise this is something people actually use out in the world. So if you see this percent nitrogen written on there, that's how they're doing the calculation. They will put the total mass of nitrogen over the molar mass of the compound, and then multiply that by 100 to get the percent of nitrogen. So this is really something that you may actually see in the real world. Like here, if you see this like lawn fertilizer, if you went and bought this, it has these numbers here. Those numbers, and it's always in the same order. It's always nitrogen, phosphorus, potassium. So that tells you what percent nitrogen, phosphorus, and potassium you have. So you can actually go through and figure out which fertilizer might be best for your lawn or whatever other crops you're trying to grow based on these percent compositions. So it's pretty cool, actually. I would pause here and then work on problems 27 through 30 on your lecture worksheet so you can get some practice with this percent composition stuff.